will tell us about the loop Hecke algebra and charge conserving Yang-Baxter operators.
Okay, yeah, thank you very much for the invitation to speak here and for moving me up a little. Appreciate that. It's what I want to tell you about is some joint work. And maybe I should preface it by saying it'll be a bit different than things that you've seen so far. So maybe it'll look a bit more classical. It'll be a bit more maybe elementary than some, but I promise you there's some relationship with all of this, and hopefully we'll see it. So, so let me start by overselling it a bit. Let me say the following. So some kind of motivation for what we'll talk about. So we kind of know the following story, that if you start with 2 + 1 TQFT, that from these you get lots of things, and in particular you get braid group representations, and I'll say a little more about that. And you get like 3-manifold invariants, and there's also a connection. Maybe I should just something like this, and then sort of the categorical side, which probably should be adjacent to this one, is like modular tensor categories. And so we have this sort of setup, and this is sort of the 2D version. And I'm interested in what happens if we change to 3 dimensions. So in 3D, right? Well, you start adding numbers. So TQFT, and over here, maybe 4-manifold invariants. There's something here. Maybe it's a little harder to express. What goes here is I'll just put some categories, maybe spherical 2 categories or something along these lines. But then you might wonder, like, well, what goes here? Right? What's the sort of analog? Well, let's briefly talk about the braid group. So see one perspective that will allow us to sort of generalize this. And so one way of thinking of the braid group is that it is the group of motions of a collection of points in the disk. Okay. So what do I mean by that? I just mean, well, you have your disk, and you can define something, and in fact, it's been done. You have a bunch of points in the disk, and you kind of, well, it's the group of motions. So that it comes from some diffeomorphisms or homomorphisms of the disk, and sort of these points need to land where they started, they're unordered. So just the set of points needs to be preserved under these things. So this is a way of thinking of the braid group. And so this way of thinking of the braid group allows us to generalize a little bit. And so that's what we'll do here. So this here will be motion groups of 1-manifolds in say 3-manifolds, and maybe let's just take S3. So that's the idea here. So we have the braid group, and maybe a nice generalization would be this. So what does this sort of thing look like? Well, let me remind you what the braid group looks like. So it has it's generated by sigma 1 through sigma n minus 1, subject to relations. The first braid group relation is sigma I plus 1, sigma I plus 1 is equal to this. So this, everybody maybe knows this. Just write it down. I missed something. Yeah, thanks. Just fine. Yep. Yeah, you barely read it and then hard to be wrong. And then also far commutation, which says that the commutator of sigma I and sigma j is 1 if I minus j is big enough. Okay, that's the braid group. Okay, and so what we'd like is, well, think about these motion groups. What can you do here? So let's take a very specific example of the following setup. So we have a bunch of free loops, and I'm going to orient them to get rid of some symmetry sitting inside, say, S3, or I don't really care, it could be R3. And so I want to understand the group of motions of this. So this is possible. So what are the motions here? Well, you can think of some, right? So, right, here's a motion, right? So it's as a set, it's preserved, okay? So that's a good one. But, right, these have topology, so interesting things can happen. For example, you could push this one through and then keep going. You can think of it as a motion in this way. So you can think of the exchange as sort of happening with time, maybe something like that. And so they're tracing out a couple of like tubes, maybe, that have been cylinders that have been crossed. But this one's a bit more complicated. You can't really draw it, especially on the board, or if you had three-dimensional chalk, you still couldn't. You still need projections because it's all happening with time, right? And so forth. So that's another motion. Because I've oriented them, this is no good. Okay. And it turns out that's it. And you can write them down. And in fact, in this particular case, the motion group will act faithfully on the fundamental group. And so you can, S3 minus 2 or however many loops. And so you can actually do this at home. Just, right, get some yarn and give yourself some, right, fundamental group generators, play around with these, and you can work out relations. Okay. But I will save you the trouble and tell you what the relations are. And so what is this called? This is called the Loop Braid Group. And so it has two kinds of generators. We have what I'll call sigma I, and you'll see why in a moment, which is the sort of the leapfrog thing of I through I plus first. Okay, so that was the second motion I told you. And I could draw a picture, but it would sort of not be very representative. It's probably better to just keep in mind what I did. And then you also have the other ones, SI, which are the, I guess these are sort of loop permutation. Okay, so these are the generators for this. And now let me tell you the relations. Let me do it. Yeah. The relations are that the sigma I satisfy B1 and B2. Okay. Remarkably, maybe, but if you just use these, if you sort of ignore the flip, they satisfy both of these. Okay. The SI satisfy B1 and B2, sort of interesting, and their squares are the identity. The reason is, if you do this, twice in 4 dimensions, there's enough room to undo it. And so what is this really? This is Sn. It generates a copy of the symmetric group Honin letters. And then there are the mixed relations. Okay, so what are the mixed relations? So they look a lot like this, just where some of the sigmas turn into s's. So I'll write down what they are. So they are Si plus 1, sigma I is equal to sigma I plus 1, Si plus 1. Okay. And I'm telling you, you can really actually check these if you believe me that the fundamental group is acted on faithfully. The other one is sigma I plus 1. Si is equal to Si plus 1, sigma I plus 1. you might look at the symmetry of these things a little bit. It turns out that it doesn't really matter where you put the sigma here because these have order 2. You can kind of move things around a bit. So you might think of other relations, but there may be consequences. This one, if you were to start with I plus 1 here and go switch those, doesn't hold. So that makes it, slightly interesting. Now, you can replace this one with the relation where you start with I plus 1 and get a group that's isomorphic, but you don't include both of these, okay? So there's something called the virtual braid group, right? Which this is a quotient of, it turns out. The virtual braid group just has this relation. This and the other one, like it, are called forbidden moves. So in this case, we have one of the forbidden moves is not forbidden and the other one remains forbidden. A bit confusing, but anyway, these are the relations. Okay, so right. So the question that we want to think about here is, yes, sorry.
What about the parallel relation between the sigma and the s?
Yeah, thanks. Definitely need that. Sigma I S J commute I minus J. Thank you very much. Yeah, so far commutation as well.
What's the theory that allows you to say?
Thank you. What's the theory that allows you to say those are all of the relations? That's it.
Yeah, so these, I mean, it's a bit complicated. This was proved probably by Dom in his thesis in the 60s. It's a very topological.
It's also using something like surf theory.
Yeah, whatever was available in the 60s.
Oh, okay.
So it's more elementary, maybe, but beyond an algebraist like me. I mean, okay, right. So the kind of the question I'm interested in here is, let me actually just write it here. So what about representations? It's a good question, right? The point is, in the setup over here, we get representations of the braid group. Here we should get representations of the motion groups. The point is, if you hand me a TQFT, no idea how to write this down, the representations. So that's a bit of a problem. So instead, we're just going to study the representations from algebraic point of view and hope that someday it's connected in some reasonable way. Right. Of course, braid group representations were studied long before modular categories were defined. So at least historically, we're following the right path. Okay, so representations of this. So one of the important things to notice is that it contains the braid group. Okay. So a natural thing to try would be to lift representations of the braid group. So that's one approach. So lift Bn reps. So what ones can we think of? Right. So this gives us a whole industry of trying things. So you could try, say, the Rowell representation. Okay. And indeed, you can write down a lift. What do I mean by a lift? Just the Rowell representation has, dimension n. It's the same n, and just tell me where the SIs go so that all the relations are satisfied. It's also an n by n matrix, so you just kind of can do it. And it's a pretty natural thing to do. You might wonder if the loop braid group is linear. And so you might say, well, what about the Lorentz-Kramer representation? It's not, it does not extend, turns out. And then a big collection of things would be solutions to the Yang-Baxter equation. And right, so the answer here is sometimes, not always, sometimes. Yep.
I mean, rather than trying to turn the S's, I think, into like endomorphisms of whatever vector space, are inductions interesting, or you don't want them because they're infinite dimensional, or?
Right. So certainly the braid group is not a normal subgroup.
Oh, okay. Yes.
And so then maybe, yeah, as you say, inductions could get nasty. Yeah.
So suppose you have like a tensor product of n representations of a quantum group.
Yep.
then you could define an action of this virtual braid group by the SIs just act by usual permutations of tensor factors.
Yeah.
But I guess it doesn't descend, or
So right. So there can be trouble with this. You're kind of asking like a fusion category to have two different ratings and for them to interact well. Seems hard. I tried a few and
Maybe innocent question, but do you have an exact factorization between the permutation group and the braid group, or is like something that generally mix?
they're really mixed. Yeah.
Okay.
Other questions? Everybody? I'm glad people are enthusiastic about this group. It's been, so it was studied by Dom in the 60s and then by Goldsmith in the late 70s and 80s. And then it was like forgotten for 20 years. And then people like in 2006 or so started thinking about it again. Baez and his group thought about Baez, Kranz, some other people. Anyway, I think it's quite an interesting one. Right. So this is a question. We addressed this one in a paper with sort of, well, me plus Zhenghan Wang and a group at Leeds, so Kadar and Martin. Zoltan, Kadar, Paul Martin. Sorry, I'm not sure why I'm using first and last here, but anyway, yeah, so we studied this question and that was the answer is sometimes. Okay. So this is one approach. Now, there's another way. So we can try to lift representations, or we can be inspired by the representations of the braid group. So another approach would be to think about so finite dimensional quotients of the, say, group algebra of this group. Okay, this is something that for braid groups has been done a lot. Hecke algebras, BMW algebras, well, etc. These kind of things. There are ways of doing this. And so this is what I would like to think about, at least what we thought about to start with, is trying to find finite dimensional quotients. So you might ask, right? So the first try would be, well, let's just take the Hecke relation, which is you mod out by the ideal generated by sigma I minus 1. Make sure I don't get the plus and minuses switched. I guess I'm okay. Plus T. Right? You might try this. If this were just the braid group, this would be exactly the Hecke algebra. But unfortunately, this is infinite dimension. And so you look for more things. And essentially, the brilliant idea that Celeste Damiani had, my co-author on this paper, along with Paul Martin, was to look at the relations that the Rowell representation lift satisfied. And it turns out that this does the job. So instead, so let me call this one Hecke 1, let's say. So second try is that if you take and quotient out by Hecke 1 and two more relations that are sort of mixed, then we're in business. And the two relations are, so I don't get them wrong, sigma I minus 1, Si plus 1, and Si minus 1, sigma I plus T. And we define this to be the loop Hecke algebra, okay, in this finite dimension. It's a really interesting algebra. It's non-semisimple, okay, and we can prove it's finite dimensional, but we only have a conjectural guess of what the dimension is for many of the numbers. So let me say just a little bit more about this. Let's see, erasers. Yeah, so this is the idea. Okay, so this is the loop Hecke algebra. And so now, of course, it's finite dimensional, which means if you understand its representations, suddenly you have a wealth of representations of the loop braid group given by these, however this thing decomposes. So, so we have a conjecture about the dimension. So conjecture is that the dimension of the loop Hecke algebra is equal to 1/2 this number, and this is assuming t squared is not 1. Otherwise, there's some different things that happen. Okay. So that's the dimension, and so this is true for n less than or equal to 7. So probably it's true, right? Seems like that. Okay. Now, how do we prove this? Well, you can do some kind of computations, but it turns out that we have a representation of this algebra that we believe is faithful. And it's a representation that comes from lifting a solution to the Yang-Baxter equation. So we circle back on that idea a little bit. And so, right, so here's a representation of the loop Hecke algebra. And what is it? Well, it's exactly of this sort of Yang-Baxter form. So I'm going to define R of T to be the following 4x4 matrix. So it's 1, and then there's a middle square here that I'll describe. 1 minus T, T1, 0, minus T, and everywhere else 0. Okay. And then if you send sigma I to the identity tensor I minus 1 times tensor R of T, tensor the identity the right number of times n minus 1 minus I think. Sorry, you can't read that anyway, but anyway, the right number of times. And you send Si to the same thing, but evaluate R at 1. Right? Same thing. This does the job. This is a representation of the loop braid group and factors over the loop Hecke algebra. Now, this is a kind of interesting one. You might wonder where this comes from. So this is just the universal R matrix after some reparameterization of UQ. There's a lot of people here that know this stuff. Any guesses? No. Has anybody seen this one? The first guess is SL2, and it's not right. Yeah, so it's SL. Yeah, 1,1. Exactly. Yeah. If this were a 1, then it would be essentially the UQSL2. That's a minus. Whatever it is, whatever your notation is, bar. Yeah, bar is better, I agree. Yeah, it's the super thing. Yeah. So interestingly, right, we found that if you take at UQSL2 R matrix, it won't lift, but this one does. Interesting. Okay. So that intrigued us. And so we sort of, right, why this one? Right, that was like the question that sort of we came up with. And yeah, so anyway, this representation is conjecturally faithful, and that's how you get this conjecture, is we can completely analyze this representation, no problem, and write down exactly what it is. It's non-semisimple. It's, if you quotient out by its Jacobson radical, you get semisimple algebras whose Bradley diagram is Pascal's triangle. So it's a pretty interesting setup. But anyway, so that's what we have. But right, we sort of had a little attention deficit going on, and we sort of took this journey. Okay, why this one?
Can I ask
Yep.
a question? So that 2 by 2 you have in there
Yeah.
kind of reminds me of these bowling ball representations of the braid group. Is there any, have you looked at those?
So those are, I think, the Rowell representation
They're slight,
or related to the
they're
varroa.
related,
Yeah,
yeah.
yeah, it's maybe the reduced one or something. Yeah, so those ones,
I thought, yeah, for
Right.
some reason I thought I was asking a different question, but is if it's just the Burrell case that you've already.
I think it,
looked
yeah,
at,
I think
okay.
it is, yeah. Yeah, so this does give a representation of,
So this isn't a bowling ball representation, this little thing here.
yeah, it might be. I
Okay.
mean, because of this, yeah, Jones's description, I think, of the bowling ball representation is related to Burrell.
I was thinking of this paper of Stephen Bigelow's.
Oh, I see. Yeah.
Okay,
that
yeah.
I don't know. Yeah,
So,
yeah.
hey, I'll ask you later.
yeah. All right, so why this one? Well, this one has a particularly interesting, and hence the second part of the title. This one is so-called charge conserving. So let me define what charge conserving is. So I'm going to define it just for two copies of a vector space. So I have some T and an endomorphism of two copies is charge conserving if I look at the sort of subspace labeled I by ij, defined to be the span of EI tensor EJ and EJ tensor EI. So if this is preserved by T for all pairs I and J, potentially I equal J. So charge conserving. So you're kind of thinking of I plus J maybe as being the charge, right? There's a good reason to think of it in this way, sort of going back to that idea. So notice this one is charge conserving because, right, E1 tensor E2 or maybe E0 tensor E1 and E1 tensor E0, that's sort of this little matrix here. That's just moving that part around. And, right, E1 tensor E1 is preserved, the subspace, and same with E0 tensor E0. So this is charge conserving. So this is a general definition. And so here's the problem. Classify charge conserving solutions to the Yang-Baxter equation. And okay, so that's sort of the question. And this is what we were able to do. So let me say a little bit about classifying any kind of solutions to the Yang-Baxter equation. So it's in general a pretty hard problem because so what's known? So Hayatarinta in the 90s, early 90s, classified all solutions to the Yang-Baxter equation that were 4 by 4. And that continues to be the best we know. Yeah.
Why won't the usual SL2 R matrix be charge conserving?
Yes, it will.
Oh, I thought you said that one was no good.
It won't lift.
Oh,
Right. But it has this special form. And so it's kind of like, why that one and not this one? They both have that. And so that was sort of part of the inspiration. Yeah. Yeah. So sorry, the story maybe isn't as cohesive, but it's like real life in that sense. Yeah. Okay. Okay. Right. So let me tell you how to handle this. And in order to do this, let me I'm just going to hold this up briefly so I can write and then I'll put it back down. So if I have such a T, I can describe it by a sequence. So let's say, say the dimension of V is capital N. Okay, just that's dimension. So to encode charge conserving operator, I just need some numbers, A1 through AN. Those correspond to when I is equal to J. It's a one-dimensional space. And then I've got a bunch like A1, 2, A1, whatever. Well, I'll stop there, etc. And then the last one is A n minus 1 n or something like that. Okay, so there are n choose 2 by 2 matrices that I need to tell you. Okay, that corresponds to when I is not equal to J. So I can assume, of course, I is less than j, and so that's how many there are. And then these are just the one by ones. So to specify any charge conserving operator in this setup, that's all I need. So I'm going to tell you how to get all of these things so that it satisfies the Yang-Baxter. Okay. So, right. So before I do that, I should say, okay, I'm going to stand over here. So I need to, oh, okay. Yeah. So let me erase here. Yeah. So, let me tell you about the symmetries a little bit of the charge conserving Yang-Baxter operators. So some symmetries. So a lemma maybe. So say X R X. So let me say let R be a charge conserving Yang-Baxter operator. Then X Rx inverse is also if one of two things happens, X is diagonal or X is a Herm matrix of the form Q tensor Q. Okay, so R acts on two copies of V. So if X is any diagonal, still true. If X is a tensor product of two permutation matrices. Now you might say, hey, wait a minute, I can conjugate by any old matrix of this form. It will still satisfy the Yang-Baxter equation, but it won't be charge conserving in general. So that's what we need to do. So there's kind of less symmetry here, but this symmetry isn't true for general solutions to the Yang-Baxter operator equation. So there's kind of more as well. So these are a couple of symmetries that there are. Okay, so now I think we're ready to. So I'll be describing the solutions up to these symmetries. And so let me say that. So we have a combinatorial way of describing these things, and so here's how it goes. So we start with some individuals. So the combinatorics here are the following. So we have n individual, 1 through n. And the n is sort of the same. Okay, is blue a bad color? Maybe it is.
Yeah, a little bit. Yes.
Okay. So n individuals, which are 1 through n. Okay. And now I'm going to partition these individuals into nations. So partition into nations. Okay. And let me give a name to the nations. Say N1. So it's terrible notation, different sort of N, but whatever. It's nations. So what are you going to use? So there's maybe K nations. Okay. So you just separate these individuals into K nations. And then you're going to partition nations into counties. Yeah, English co-authors, not states, not provinces, but counties. Right, so like in I will be the disjoint union of say Cij for some number j. Okay, and there's one more thing I want to add here. I want when you do this, just it isn't necessary, but in order to get closer to a transversal, we will assume that this respects order. In other words, individual 1 is in nation 1. Individual n is in nation nk. Same thing here. As I partition in 1, individual 1 goes in county 1. So this will also respect order. Okay, and so now I claim that for any such thing, I can give you a charge conserving Yang-Baxter operator, and moreover, any charge conserving Yang-Baxter operator can be constructed in this way up to these symmetries. Okay, So I should be slightly careful here. When I partition into nations, anyway, it won't be quite a transversal. There's some weird reasons, but it's almost. So now I need to tell you how to construct a solution to the Yang-Baxter equation from these. And well, I'm going to tell you what A1 through AN are and these matrices. Based on the relationships between the individuals of this world I'm talking about. Any questions so far? Is the combinatorial kind of understandable?
I had a question, Eric. And when you say respects order, are you just saying there's an order preserving set function, but like in one direction?
Yeah.
Okay.
Yeah, that's right. Yeah. Right. And again, this I don't really have to do this. What I'll describe, it'll still work, but just to be closer to transversal, so we can count. We do it something like this. Okay, so let me. Sorry, I forgot one thing. There's a third thing that we must do. So that's 1, 2, 3. We're also going to color counties. One of two colors. Okay, and I don't know what colors are going to be best. Can you see that? Let's see if red's any better. Red's better? Okay, good. Okay, so yeah, that's an unfortunate thing from my perspective, but right. The color county is one of two colors, and the first county always, you guessed it, red. Okay, so yeah. Okay, so let me just give a picture of this. So you can draw these as kind of generalized Young diagrams. And so they'll look something like this. So let me give an example here. So, right, maybe something like this. So that would be like nation 1. Here's county, nation 2, nation 3. I don't know this. And then, right, the requirement is first one's always red. Okay, and potentially this one could be red too. Just so this is an example of such a thing. And so let me show how this this correspondence goes. So the first thing to do is for I in county ST, AI, so this diagonal thing, will be equal to alpha sub S. So S refers to the nation, or beta sub S. This is if CST is red, and yeah. Okay, so that's the first piece of information. Okay, and now for I'm going to tell you how to do the 2x2s. So here's the sort of the chart. This is what the AIJs will look like. And then there's going to be some parameters associated with these things. So if I is in nation S, and which is not equal to nation T, and J lives in there, then here's the matrix. So what is this saying? This says I and J are in different nations. Okay. Then the matrix, 2x2 matrix, will look like mu sub ST, mu sub ST, diagonal like this. And here, you just have these things. For each pair of nations, you've got a variable, okay? And of course, non-zero, okay? So those are some parameters that show up. If I is in county SX, which is not equal to county TX, and J is in there, so they're in the same nation, but different counties. Here's the matrix. It's alpha S plus beta S minus beta s alpha s 0. And there's a condition alpha s plus beta s should be non-zero. Otherwise, it sort of looks more like that one. Okay. And then finally, there's one more possibility, and that is that I and J are both in the same county. Then your matrix will look like gamma 0, 0, gamma, so diagonal. And here, gamma is one of two things. It's either alpha sub s or beta sub s. And that is, this is the red case and the not colored case. Okay. So this is the description of a solution for any such setup. Okay. Now the theorem is, well, that is part of the theorem.
I have a quick question.
Yeah, go ahead.
So you said the alpha the alpha and beta, so they indexed by the nation or the county?
By the nation.
So I guess in the middle thing it should be alpha sub and beta x.
Let's see, did I make it sx and sy? Yes.
Okay.
Yeah, thank you. Yeah.
All right, thank you.
Sy. Thanks for that. Yeah. Other questions, clarifications?
Does that make it alpha x and alpha and beta, or are they they're all indexed by s? Yeah.
Yeah, s. It's always the nation. So there's like you assign variables. The alphas are assigned to nations. Some sense. Yeah.
So is there one choice which gives the R matrix for SL2 and another one which gives our SL11?
Yes, that's right. So that would correspond to whether if they're both red, like if you had like this and they're both red, that would be SL2. If they're different colors, then that would be, yeah, that corresponds to SL2. Yeah. Okay. So the theorem is, this is a solution. That's theorem A. Theorem B would be every solution is obtained in this way up to the symmetries I just erased. And so let me just write that down. Theorem. These are solutions. So that's theorem 1, theorem 2. Every charge conserving Yang-Baxter operator is equivalent. These and 3, this essentially. So when I put the word essentially and it makes it meaningless, but I think you know what I mean, is a transversal of the orbits under the symmetry. Okay, there's some slight thing. It's really a multi-set that you have to think about. And anyway, this is the idea. So that's so we have a complete classification of charge conserving Yang-Baxter operators. Okay. So I have 3 minutes to. So all this is stuff I said in Paris in June. So some of you were there, and it was maybe not a terribly complete story because you're like, hey, what about the Loop Braid Group? Well, this is your promise, right? So now we can complete that. So this is in ongoing work with Paula Martin and Fiona Terzuska. I'm probably saying that wrong. It's at least spelled right in my brain. Okay. Yeah, and so it's a number of things. And here's the idea. When do these lift to charge conserving sort of loop Yang-Baxter? Okay, so in other words, when can you find a matrix S to go along with the R that I've described that gives you a representation of the loop braid group in the sort of obvious local way? And the answer seems to be so if and only if each nation has at most 2 counties, and each if 2 counties distinct colors. So for example, if I have something that looks like that, and maybe I've got some more, something like this one would lift. But if I have more counties, it won't lift. And moreover, if this county and this county were the same color, it wouldn't lift. You can have as many nations as you want, as long as they each individually obey this rule. And we also have an idea about how many parameters there are. It turns out you get parameters for distinct nations, but within a single nation, there isn't much going on. So we can not only say when it lifts, we can also classify all such lifts. And let me stop there. Thank you.
This may be a bit, I don't know, not related, but I just noticed that the dimension you propose as a conjecture is very similar to the Catalan number. So I don't know. Have you thought about that? Maybe there is some relation.
Yeah, it isn't quite. I guess it would be 1/n instead of 1/2 or something.
Yeah, but
yeah,
it also seems like you have some trees there. Catalan number counts that. So I don't know.
Yeah. We've tried a few things. We haven't really made much progress. I'd be very happy to see a proof of this conjecture. I was sort of happy enough when I verified it up to 7 and sort of, it's.
How did you verify that in low dimensions?
Magma.
Oh, there's an algorithm for that?
So you compute the dimension, you can compute the dimensions of non-commutative algebras, and their representations in Magma, if you just have relations. And then we have an explicit way of doing it, by hand for the image of this representation we claim is faithful. So that we can complete that. So the dimension I gave is absolutely right for that one. But then for this non-semisimple algebra, the Loop Hecke, it's a bit complicated. So we just throw it in a computer and hope for the best, and it dies at 8 or something.
So you say here Loop Yang-Baxter, is this related with the loop braid that you were saying?
Yeah, so I didn't have time to explain too well what this really means. All this means is that you have a pair of matrices, R and S, both of which satisfy the Yang-Baxter equation, both of which are charge conserving and form a representation of a loop braid group in the way that the one that I did give you does.
So you could define this notion for other motion groups.
Yes, by all means. So in fact, you can talk about charge conserving representations of whatever, right?
Okay.
Because it's just about the matrices,
matrix.
as long as it sort of operates on tensor powers of something. Yeah, that's right.
So, like, for instance, this representation you just wrote up, I mean, is this something quantum groupish, or is it far from quantum groups?
Well, so, I mean, this one individually is essentially UQSL 1,1, right? So it's definitely quantum groupish. If you take UQ, so backing up to this situation where it's not loop, but just the braid group, all of the UQSLN representations are charge conserving. So lots of quantum group things are charge conserving. We really don't have we just produced this, so we haven't carefully thought about, what else what are these really doing? Are they like centralizers of something nice, right? Like we might expect. In some cases, obviously, the answer is yes, because it's like, oh, this is, it's the Hecke algebra or something temporally Lieb. So yeah, so this is a great question. We really wish we knew. The fact that it's non-semi-simple these days, of course, is a feature, not a bug. And so we're really hoping that maybe these do describe centralizers of some non-semi-simple.
Any further further questions? If not, let's thank Eric again.